Hello everyone, welcome to this lecture of the course Digital Electronics and Circuits, and in this particular lecture we will be talking about another set of sequential elements called registers. Sure, and in this if we talk about registers we will talk about two kinds of register, normal registers and shift registers. And additionally when we talk about registers we will talk about a concept of clock gating as well as a concept of parallel loads. Let's get started with it. Let's draw a basic register structure. Basic registers are very easy to build and we can store multiple bits just by pushing a bunch of flip-flop together. If we have to draw a diagram, right, a black box diagram, it would look something like this, where we have a clock input, we have a clear input. We will look at usage of clear in some time. We have a set of inputs. Let's assume we have a 4-bit register and then we have 4 outputs. Correct? And this circuit would look like something like this. So we are having, when we say that we are looking at a basic register, a 4-bit basic register, what that would mean is we would need 4 flip-flops. So let's assume we have 4 D flip-flops over here. Right, and basically each of these registers has D, C, and this is the output Q, D, C, output Q, D, Q, C, D, Q, C. Right, and C is nothing but each of this C is connected to a same clock. Basically what we can say is it's connected to the same clock, and let's assume is a positive edge trigger D flip-flops. And what we will have is we have an input D3, we have an input D2, we have an input D1, and we have an input D0. Now whatever we spoke about clear, right, this is a reset pin of D flip-flop. We spoke about these pins, set and reset, right? Correct. So now if we look at this particular circuit, right, what is happening over here, whenever clear is equal to 0, or we can say whenever clear is equal to 1, as the name says clear, whenever clear is equal to 1, reset for this particular flop would be active, and all the outputs Q3, Q2, Q1, Q0, Q2, Q1, Q0 are nothing but 0, 0, 0, 0. Right? So basically whenever clear is equal to 1, output is always, these are the outputs. This is Q3, this is Q2, this is Q1, and this is Q0. So all the outputs are 0. And whenever clear is equal to 0, in that particular case, on passage of a clock, Q3 will get a value of D3, Q2, Q1, Q0, right? This will be the basic operation of a circuit, right? But what is happening in this particular case is, right, whenever we do a clear, output is 0. Whenever the clear is not there at passage of the clock, Q3 is equal to D3, Q2 is equal to D2, Q1 is equal to D1, and Q0 is equal to D0. We are not able to store this value, right? Correct. For more than one clock cycle, say at one passage of a clock, we have multiple clock edges. And let's assume clear is 0. It was 1. Clear became 0. We have multiple clock edges. And in case input is toggling, right? Say let's assume D3 only is something like this particular. In that case, what will happen is always at a passage of a clock, this always will be 0 output. At passage of a clock, value of D would be sampled and given to output. So basically output would toggle at every change in D, but we will not be able to hold the output for one more than one clock cycle, right? So what we have to do in this circuit to be able to hold the value of the inputs for more than one clock cycle, right? What we will do is we will add a new signal, add loads input. We will add a new variable called a load input, and the condition would be if load is equal to 0, register keeps its current contents, but if load is equal to 1, right, the register stores a new value taken from input. Correct? So this circuit would look something like this, where we have set of inputs D3 to D0, we have set of outputs Q3 to Q0, and we have now multiple set of signals. One is a clock signal at the edge trigger one was the clear signal as we saw previously, and one is the load signal. So load signal is a new addition, right? And the circuit would operate such that if load is equal to 0, Qt plus 1 would be equal to Qt. It will keep its current contents. That's when we will be able to say that even though clock is changing, or even though the input is fluctuating, output is basically it has restored its value, right? It is not moving at all. Whenever load is equal to 1, q of t plus 1 would be is equal to d3 d2 d1 d0, which is equal to input. So this is a case, right? And I hope this is clear, right? We draw a simple 4D flip-flops back to back. We said, okay, it's a 4-bit register. We are looking at it. We had a clear signal. Whenever clear is equal to 1, output will be all zeros. Whenever clear is equal to 0, D3 is transferred to Q3, D2 to Q2, D1 to Q1, and D0 to Q0. But what we said over here is whenever there is a change on the clock edge, whenever there is a clock edge, and if any change on the D inputs would be reflected on the Q outputs. But for a register, right, we don't need this. Register should be able to hold a value, and it should be able to retain a value as well. For that, what we did is we said let's add a load signal, and what this load put will tell us, like whenever the load is equal to 0, a register will keep its present contents, and whenever the load changes to a value 1, register will be able to store a new value taken from the inputs. And this will be a sort of characteristic equation where we say when load is equal to 0, the next state retains the present state, and whenever load is equal to 1, the next state is equal to the input, right? And how do we implement such a circuit? That's pretty easy, right? We already spoke about 4D flip-flops being present back to back, right? So basically this is my flip-flop number 3, flip-flop number 2, 1, 0. So basically this is Q3, Q2, Q1, Q0. This is the input, right? D3, input D2, input D1, input D0. And then we have a set of reset pins everywhere, right? This is reset. These are connected to not of clear bar, right? We already spoke that we have a clear signal. These are connected to clear bar, and we have a clock inputs for all of these, which is connected to same clock CLK. Same is connected here to CLK. Right? Now we have a load signal. What we will do is this particular CLK signal would be something like this, which I will show you right now. What we will do is we will take the load, we will knot it, and we will OR it with original clock signal to form these clock signals. Now what will happen in this particular case, right? As we discussed previously, whenever clear is equal to 0, output is equal to dependent upon is function of input, right? And whenever clear is equal to 1, clear is equal to 1, output is always 0. Now basically output is a function of input. How? Basically whenever clear is equal to 0, now what is happening in this in this particular case, right? Now let's assume if load is equal to 0. If load is equal to 0, load bar becomes 1. If load bar becomes 1, this output of this particular gate is clock is equal to 1. So basically in this particular case, the clock signal will remain 1, irrespective of what is this particular clock value, right? So let's assume what happens is we had a normal running clock, and what we do is we make load is equal to 0. It remains as 0. If at all it remains at 0, what will happen to this particular CLK? CLK would look something like, whenever it was 1, right, it was like clock. CLK would behave like this. So irrespective of whatever pause edges was there, right, these pause edges would be ineffective, because this particular clock would be only getting a value at this pause edge. So basically Q3, Q2, Q1 and Q0 would obtain a value of D3, D2, D1 and D0 only at this pause edge, and whenever it stays 1, right, this output will remain is equal to this particular value which was taken at time t, and it will not change irrespective of whether D3, D2, D1, D0 changes or not, because this particular sampling would be at this edge only. These edges will no more be seen, correct? And whenever a load value becomes 1, whenever a load value becomes 1, clock will be behaving equal to clock, right? And in this particular case we will see a normal behavior where all the inputs are getting transferred to the output. I hope this is clearer, right? This particular concept is clearer, and this particular concept is called as clock gating. Basically what we have done is we have stopped clock, and but usually it's not recommended to do such kind of operations and to leave the clock as it is, right? Let's assume that what happens if at all we don't want to change the clock. We have a load signal, right? But we don't want to change the clock, we don't want to mess around with the functionality of the clock which are input to this D flip-flops. Is there another way out, right? Yes, there is another way out, and let's look at that particular signal, right? So the circuit we had till now was 4D flip-flops, one flop for each bit. This is 0, this is 1, this is 2, this is 3. Let's assume this is a reset which is connected to clear bar, and let's assume this functionality is present everywhere. Let's assume all of them have proper clock, and which is connected to a proper clock input, right? And what we need to do now is, this is output Q3, this is output Q2, this is output Q1, and this is output Q0. What we need to do now is, whenever load is equal to 0, output should retain its value. At t plus 1, it should be able to retain. When is equal to 1, all these at t equal to 1 should be equal to the input. and we don't want to mess around with the clock, we don't want to change the clock, we don't want to do clock gating anymore, right? So what does this mean? This means that depending upon the load signal, we have to select between previous state and the input D. Have we seen a circuit like this? Have we seen a combinational circuit like this before? Remember, we had something like, right, we looked at this nomenclature and we saw called this circuit as a multiplexer circuit. Basically, depending upon the select line, one of these 2 raised to power inputs will be connected to output. So basically, if we draw a mux circuit, right, a multiplexer, what does this would do is this output would be either Q3 or D3 depending upon the load, correct? Now let's assume this is a select line of a mux, and let's assume we connect this select line to load. If load is equal to 0, my previous state should be retained. If it is equal to 1, D3 should be coming out. And what we will do is this operation we would enter over here. Would this solve the purpose? Yes, this would, because once load is equal to 0, Q3 will be transferred over here. So D3 will be equal to Q3, and my output, basically Q3 would be equal to D3 and my output would be stored, right? Nothing would change over here. Is this clear? Sure. And similarly, the same thing could be written for all the other circuits also, where we have to select between D3 or the Q state, where the Q state is a previous state, right? If let's assume when load is equal to 1, what would happen? We will never look at Q3. Any input is reflected at the output over here. But whenever load is equal to 0, Q3 value over here would be Q3 at time t, right? So basically what will happen is at that particular time instant t plus 1, so basically Q3 at t plus 1 would be equal to this input, which is nothing but Q3 of t when load is equal to 0, right? So basically this particular circuit is called a resistor circuit with parallel load, and we used a multiplexer to implement it, correct? I hope this is clearer. And basically, just to recap, what we did was we started this lecture saying that we will talk about resistors. We spoke about a resistor, we built a resistor, and then we spoke about a concept of clock gating and parallel loads to realize a resistor where we are able to save the value for more than one clock cycle. This is a basic circuit we analyzed. Then we said, okay, at the load input we need to have a load pin, and this was the particular functionality which we wanted to achieve, and we were able to achieve it using a clock gating circuit, where we said, okay, let us or the knot of load with the clock and create a new clock. Depending upon the value of load, clock will either toggle or not, but usually playing around with clocks is not at all suggested, because there are multiple other things which a clock might drive in the circuit. So what we did is we said, okay, let's look at a parallel approach, where we said that, okay, let's look at a parallel load, where we what we will try to do is, depending upon the load signal, since our output should vary, right, we implemented a mux, and that mux solved our purpose. And similar muxes would be captured over here also. For example, what I mean is there would be something similar over here. This will be the output, this will be equal to load, this will be equal to D2, this will be equal to Q2, so on and so forth, right? Now let's look at a concept of shift register. Okay, so when we talk about shift register, right, what does that mean? Correct. Let's assume that we have a set of serial inputs, right? And I want to send out a set of serial inputs on the outputs one by one, right? So basically shift registers are used to implement this particular functionality, right? So basically this means that they are able to shift the output once every clock cycle. Sure. So just to show you an example, right? We just now looked at a circuit where we had 4D flip-flops back to back. Let's assume that circuit here only. Assume these are 4D flip-flops with proper clocks, inputs, Q bars, correct? Now let's do one thing. Let's have a serial input over here. Or we can say it as shift input also, right? So let's assume all of them have proper clock. They are connected to same clock, right? And what we do over here is, right, what happens in such a case? If we do this, this is D, this is Q, so on and so forth. It's D, this is Q, this is output, right? Let's call it Q0, call it Q1, Q2, let's call it Q3, correct? Now what will happen in this particular case? Q3 at time t plus 1 at a clock edge of clock will be equal to SI, correct? Q2 at t plus 1 would be equal to what? The value of Q3 at time t. Q1 at t plus 1 would be equal to what? The value of Q2 at time t, and Q0 at time t plus 1 would be equal to what? This will be equal to value of Q1 at time t, right? So what is happening? Let's assume my present state Q3 to Q0 was what? Let's assume it was 0 1 1 0, and let's assume that input, serial input SI, was 1. What would be my next state? Next state would be Q3 would be equal to SI 1, Q2 will be equal to Q3, this one 1 1. So basically what is happening from present state to next state? This LSB has got removed, or what we can say is the expression has undergone a right shift, correct? So Q0 got lost. So what we saw was Q0 got lost, which is equivalent to right shift. That's why it's called a shift register. I hope this is clear, right? This shift register concept is clear. And one of the use of the shift register is when we are getting a serial output and we wanted to send a serial input and we want to send it on an output, we can use this shift registers for that particular purpose. Now, if I say that, okay, this was a right shift, how can we realize a left shift operation? So basically right shift or left shift depends upon how do we take nomenclature, whether we speak that, okay, Q3, Q1, Q0 is like this, or we say Q0 is the MSB, Q1 is the next one, Q3, and this is the LSB. So depending upon whether we treat this as MSB or this as MSB, we can either build a right shift register or a left shift register. If at all we want to left shift register, right? If at all we want a left shift registers, so what we will do is we will replace this Q3, instead of Q3 we will make it Q0, and we will get a left shift register. Hopefully this lecture was clearer, and the concept of registers, shift registers, parallel load, and clock gating is clear to you. Thank you for attending this lecture. See you in the next one.